Okay, thank you for a very good presentation, Stephen. I will try to also keep time. I'm quite sure I will be able to do it. I will give you a little bit more information about practice and common mistakes and the state of knowledge also in Sweden. I don't only work at the company called SKANSKA, I also lecture at Lund University. And this is a standard, simple example I always give them to be able to understand how to grasp the concept of thermal bridges, which I believe is very important. They always first have to start with discussing in group if this is an actual thermal bridge, only seeing this kind of picture. And then they get the equation, as you can see out to the right, and then they get the task to quantify the thermal bridge based on internal and external dimensions. And as you can see here, down below, I have given all the possibilities here: internal dimensions, overall internal dimensions, and external dimensions. And as you can see, quite naturally, if you use overall internal measuring or external measuring, the specific value for the thermal bridge is 0 watts per meter in Kelvin. But if you use internal measuring, the value is 0.09 watts per meter in Kelvin. So it's very important to understand it can be 0, it can be above 0, but of course, Stephen has given you the theory already, it can also be a negative value. So, how do we handle thermal bridges, and what's the state of knowledge in Sweden? I will give you some examples, and I will also show you a result from a questionnaire we did. We are actually planning to do it once more because this is actually 5 years old now. We did this questionnaire and published it in 2011. But also published it in some other magazines and so on in 2012. So how we carried out the questionnaire was that we sent the questionnaire to consultants which were working with energy-related issues. We contacted all major consultant firms in Sweden, but also some other companies, and we also checked architecture firms which had been involved in passive house designing. We sent this out to 100 consultants, and we got 79 answers, so a quite good ratio of answering the questionnaire. So to start with, we asked them, how do you measure a building element if you are going to quantify the transmission losses or do an energy calculation? And you can see that to the left, roughly 40% used internal areas, roughly 22% used overall internal areas, 29% used external areas, and 7% used a mixture or could come up with some own way to dimension it. So as you can see, a rather large spread, and that was to quantify a single building element. And we also asked them, it was a total of 16 questions, how do you define the building's enclosing area, the total building envelope? And as you can see here, there is a difference. Roughly or almost 30% used internal areas, 22% used overall internal areas, and 44% used external areas. And then you had some other ways to do it, and some people who actually didn't answer that question. And what's quite interesting already here is that in Sweden, at least, we have a requirement on the average U value for the total building envelope. And if you take a few seconds to think about this, you understand that if you quantify a bunch of building elements and then you multiply them with the U value, and then you divide them with the enclosing area. And as you can see, if you do it like this, as the Swedish engineers, you have a bigger enclosing area than the total sum of the building elements. So already here you have an error when you calculate the average U value. What I'm not going to show you here, but as you can see, you can check the article. As you can see, it's referenced above. They also had to do an examination of 6 very simple junctions to say if it was a thermal bridge or not. And these junctions were made in a way so they had to understand the differences if it was a thermal bridge or not, related to if they were quantifying the building element and the elements according to internal areas and external areas and so on. And quite roughly, 40% did not understand the concept of a thermal bridge. They couldn't handle these differences. They didn't understand the very important definition of a thermal bridge, which is if you have differences in external and internal area, you have a thermal bridge, as Stephen showed us. And also, which we also believe was quite interesting, a lot of consultants use simplified methods to assess thermal bridges. And we also asked them to then describe how this simplified method is used. And there were mainly 2 ways to do it, and also some in-betweens. But the most common ways was to, if you have quantified the U values for different building envelopes, you just added a certain percentage to your total U values. And this was quite also different. In some cases as low as 5–10%, but in general 15%, which is quite low, as we will see. So one way was to add some percentages to the U values. The other way was they said, okay, we just look at the specific part where the thermal resistance is lower, and then we calculate the U value for that part and use it as a thermal bridge. And if you do so, then you think that heat transfer is only in one dimension. So what they actually did, I don't know if you can see my marker or my pointer, but if you look to the left, you have a junction 7, because there were different junctions exemplified in the papers. They just calculate the U value. What you can see is on the left junction is an internal slab and an external wall, which have less insulation on the exterior side of the external slab. So what they did, a lot of them, they say we calculate the lower U value for this small part of the building, and then we multiply it with the height, which give some sort of value for a thermal bridge. And they did similar ways for junction close to windows, for example. This is a concrete sandwich panel, where you have concrete on the interior side in junction 8 and concrete on the exterior side, and then you need some concrete navings to be able to mount your window. But of course, this is not true. The reality is that heat transfer moves something like this, as you can see. It moves in more than one dimension. And what happens, for example, in the example with the interior slab, is that the interior slab will roughly have the same temperature as the internal temperature, which means that you have heat transfer going upwards and downwards and trying to find other ways to spread, which will increase the thermal bridge. So what we see here is maybe a somewhat complex build, but I will explain it. What you see on the x-axis below is heat resistance in the wall for these 2 junctions, which we have increased from roughly 4 up to 11 almost, which could be considered to be the patio house wall. For those of you who are more familiar with U values, this is because this, I think, was presented in an ASHRAE conference when they are more comfortable with R values. But U values up here is roughly 0.1, which we can say it's something that is very commonly used in patio houses and so on. What you can see in the light gray dots, it's if you use these simplified methods, what would the thermal bridge value be? we just calculate a specific U value multiplied with the height of the junction. It stays quite stable around 0.1 watts per meter in Kelvin. And what you can see in the gray dots, or the dark gray dots, is the actual value when we do this in considering a two-dimensional heat flow. And what you can see is the differences between these two, they differ. And that's what's presented with the axis, you could say. And this is why this is gaining more and more importance. As you can see, if we build like a standard wall, you could say, the percentage difference between making this in one-dimension or two-dimension analysis, you can see it. It's around 10 to 20%, but maybe it's not that big. But if you build, for example, a patio house and you have heat resistance around 11 or U value around 0.1, the differences between doing this in a simplified way and in a more detailed way will be around 40% for these specific junctions. So doing this in a simplified way, thinking it's one-dimensional, is not correct. So the other thing they did was they just add a percentage. They have a U value, and then they add a certain percentage, commonly around 15–20%. So to be able to address that, we checked two different options. What you can see is the alternative one is a concrete wall with an internal concrete slab with insulation on the exterior side. Until alternative two is a concrete intermediate floor with a light infill wall, as you can see, and we vary the amount of insulation. This graph is maybe a little bit more complicated, but still it's interesting and important, I believe. If we look at the first option, concrete wall with exterior insulation, the total heat resistance is the lilac or the purple line here. We add more insulation, and the total heat transmission losses, as you can see on the left side, they decrease. And we can also then calculate what's the additional losses if we would want to use the percentage factor. And this is, of course, only for the intermediate floor. And that's around 10%. And this is only based on internal measuring. That's why we have a thermal bridge, which is important to take out. You can also see the article here below. However, if we have an infill wall, you can see, firstly, the total heat transmission losses decreases. But since the thermal bridge actually increases when we do it like this, because we vary the amount of insulation to the interior side, because that's how we commonly build this, the percentages go from roughly 17% up to 60%. So if you want to add a percentage factor, it needs to be higher in this case, much higher. What's also important, I think, is to see what people tend to forget. If you see this green line, you have the same total transmission losses in this case for 200 millimeters of insulation for the alternative one, which is concrete wall with exterior insulation, but you need almost 350 millimeters of insulation if you use a light infill wall. Of course, you have other junctions, which will also affect the result, but it's very different, and the percentages are very different. To round off, I'm just going to show you this one. It's from another article, based on the first article where people were able to choose different ways of measuring and how they examine thermal bridges. We made calculations, and what you can see in the gray staples here, you can see on the left axis, it's the energy space for heating. And what you can see on the right axis, which is peak load for heating, is these crosses. As you can see, maybe if you have a lot of other things to consider, energy demand for heating, this is more or less a passive house, varies quite a lot, but since you have other stuff, it may not be so important. It varies from 20 to 30 kilowatt hours per square meter and year. However, the peak load for heating varies from 10 to more than 14 watts per square meter. And the correct way was example number 4 here, but you could end up here and you can end up with example 5 or example 1, which means that the design of the heating system could be up to roughly 40% false due to not understanding how to calculate heat transmission losses. So just to round off, I would like to say it's important to understand more insulation. It means that the thermal bridges will become increasingly important. It's possible to end up with an error of 40% if you don't understand these concepts, which may very much end up in wrong design of heating and cooling systems. The state of knowledge in Sweden at this point was not satisfying, which is very important that you need to understand because we use more and more computer tools. And what's very important also is that consultants in Sweden does not always understand that the thermal bridge may occur due to the difference between internal and external areas. With that, I am also done, and I will leave this presentation. Thank you.